Yeah, we monitor in high bloom period to monitor the gene copy number of microcystis and pseudomonas. They contains a steady state and didn't increasing too much.
Any other questions or comments, Anna?
Thanks.
Okay.
Someone is raising their hand from the attendees, but
This
I can't.
Dmitry Kirillov and Sirin and Madiar. Do you have any questions, or that you can type them in the chat?
Maybe not.
Maybe not. And I think it's already 5 o'clock. So
yes,
we reached. If there is no last question for any of the speakers, if not, I think we can close this session and move forward. So before we close, I would like to thank to all the presenters, to all the audience that had the opportunity to assist to a variety of topics within this umbrella of experimental and eco-hydraulics subjects. Very interesting presentations, I would say. I would like also to thank the members of organization, in particular the co-chairs, Anna, Monica, and Slaven. And I hope to see you all in the next IHR conferences, events. Please come to the EMI committee. We are always eager to have young blood to develop our initiatives. Some of the problems you present here required instrumentation and measurement techniques to have fully addressed on the subject. So thank you very much. Good luck.
Maybe we can also promote our session on the IHR Europe.
Please
go. So on IHR Europe, we also organize a special session. So I invite you to submit your articles, and the session is just now being updated and uploaded on the website of the IHR Europe.
Can you say about what is the special session?
Our special session is, of course, about measurements. Okay, so I just wanted to be really quick, but the special session is co-organized with a reservoir sedimentation working committee. And then the special session is focused on both on measurements in the field, in the laboratory, and sedimentation issues, including both measurements and modeling. So we try to merge these two groups, particularly for this Congress, and focusing on the measurements and modeling, specifically for sediments.
Okay, thank you, Slaven. So Marco, please.
Thank you.
The floor is yours.
Thank
All
you,
the best
Sophie,
and good luck for the session.
Really
and also,
Anna,
Manish.
Thank you.
I forgot to introduce you during when I started this session. I'm really very sorry. I forgot actually.
Okay. Thank you.
Don't worry.
Oh, I'm really very sorry. Thank you all. Thank you all the speakers and our chairs and co-chairs. See you soon during IHR.
See you soon.
Thank
all
you.
the best. And
Bye
good luck for your research. Bye-bye.
Bye.
Thank you for all the attendees. This has been the experimental methods and instrumentation and hydraulics. And
now we are moving to our next session, that is our flood risk management.
Yes.
This will be hosted by myself and my co-host Eva Fanry. And this session will be chaired by two chairs, chair and co-chair, Professor Stephen Huan and Professor Dhruvesh Patel. So from the IHR Technical Committee on flood risk management. So during the interaction with the Professor Huan and Professor Dhruvesh Patel, so speakers or the presenter, please raise their hands so Eva will make you the presenter. So that our Professor Juan is a full professor, and since 2025 is the head of the Institute of Hydraulic Engineering and Water Resources Management at the Grace University of Technology, Austria. And since 2022, he also is the vice chair of the IHR Flood Risk Management Committee and that associate chair. And our second chair, that co-chair, we can say, Professor Dhruvesh Patel, his specialization in flood risk assessment and hydrodynamic modeling and contemporary techniques such as UAV, or we can say drone, GIS, AIML. And currently he is serving as the associate professor and head of the civil engineering department and at Pandit Deen Dayal Energy University at Gujarat, India. So now I request Professor Juan, you may go through this session. So over to you. Now floor is yours, both the professors.
Thank you very much, Manish. Yes, my name is Stefan Haun. So it's a pleasure to be here at my 5th Young Professional Congress in total, so 6. So I missed one, but it's always a pleasure to be here and to chair a session there on behalf of the Flood Risk Management Committee. Unfortunately, I'm alone today because the second chair had a small family issue, so he left. He didn't need to leave or didn't join us, so I'm more or less the chair by myself. However, Eva is also here, and I know that she has also a clue about flood risk management, so maybe she can support me a little bit in the coffee break. Already said, I'm the chair, meanwhile, of the Flood Risk Management Technical Committee since this year, since June, since the World Congress in Singapore. And we are, I have to say, one of the youngest technical committees in IHR, but we are one of the largest when we have a look on associated members. So we have more than 1,000 people who are associated to our technical committee. And I think this alone shows how urgent it is to find solutions for flood risk and flood risk management, as more or less we are approaching a challenging time in the future, not only by climate change, also by urban development, by land use change, and so on. So we really need support. And this is also why we need you in the future to help and to support us. What are we doing as a committee? We're organizing webinars. The last one is just was held a few weeks ago about a dam break. We had more than 1,000 registered participants. We also publish white papers and monographs, so we are rather active. And the nice thing is, if you want to participate or if you want to join the committee, then please feel free to do so. We need your support because there are many, many things what we need to solve in the future. When I had a list on the panelist list from the people who will talk today, I saw we see a huge variety today about flood risk management. We see different methods from remote sensing, UAVs, modeling, and also doing some hydrological and hydrodynamic measurements. So you see alone by the methods what we are using, we have a broad variety, but we also have in terms of case studies a broad variety. So we are going from the coast to the rivers to the urban areas, where we are experiencing a lot of problems and a lot of challenges at the moment. But now I would like to stop to talk a little bit about the committee and like to shift over to you, as we do not only have a broad variety of topics today, we also have a broad variety of places you are coming from. So I saw there are people from Canada, from Poland, from Colombia, if I'm right, from Spain. So we have a broad variety. And I think this also makes it very nice, the Flood Risk Management Technical Committee, because we have people from all around the world. This is more or less what I wanted to say at the beginning. Now a few rules for the session for the next 1.5 hours. The EMI committee took away 3 minutes from us, but we will not be in a hurry. We will not shorten your speaking time. You have 6 minutes for each poster presentation, where I would raise my hand after 5 minutes that you know it's just one minute left. Please stay in time, because this is fair also to the others. And in the end, we also want to discuss a little bit about your presentations. When we talk about discussion, Eva already wrote it in the chat, please use the question and answer tool and ask questions. So it's not about that we are here and we ask you questions as chairs, it's that you connect to each other and then you ask questions. So please feel free, please go ahead and be very active in this session. This is not only a session from us to you, it is from you to you. So this is more or less how the next hour and then how the next 1.5 hours should look like. I see that the panelists are inside. Eva already started to share the screen, so I would like to introduce the first speaker. It's Daniel from Spain, and he will talk about a flood forecast tool based on rainfall predictions and hydrological modeling in the Francolí River Basin. Daniel, the floor is yours.
So thank you very much. I'm going to present this work that the case study is in the Francolí River Basin. It's in the northeast of Spain, in Catalonia. The methods are divided in two parts. For the one hand, we have first the risk calibration, where we identify flat events, past flat events, and of these past flat events, we obtain the rainfall fields that we introduce in our model. The model is RIPS. RIPS is a distributed hydrological model. It's a rainfall runoff model where we introduce the rainfall field of the event, and we obtain a simulated hydrograph. This simulated hydrograph of each event, we compare it with the real flood hydrograph, and by trying to make the simulated hydrograph as similar as we can to the real one, we perform the calibration and obtain the model parameters. When we have obtained the model parameters, the model is calibrated, and the second part of our work is the analog-based forecast simulation, where we perform the method that is meteorological analogs. The hypothesis is that similar atmospheric conditions, that are the hypotential fields, will both similar and produce similar meteorological impacts, that are the precipitation fields. So the objective is to identify past events that are going to call it analog events that exhibit the most similar atmospheric configuration to the studied event. So with the meteorological analog method, we obtain predicted rainfall fields for each event we are studying, and the rainfall fields are inputs as well. The rainfall fields, the predicted rainfall fields that are inputs to the risk model that is calibrated. So for each rainfall event generated, we obtain a flood hydrograph. Finally, we perform a flood forecast in the Francolí River Basin. So in the middle, the results, the calibration process was performed for 5 flat events. Here I put only an example. That's an example of the 15th of October of 2018. It's a very good calibration where you can see that the real hydrograph and the simulated hydrograph are very similar, but not all the calibrations were so good. For example, 2 calibrations were worse. So we consider these 5 calibrations to obtain the model parameters. When we have the model parameters, we perform the hydrological simulations for other 5 flood events. For these hydrological simulations, as I said before, we use the precipitation field forecast derived from the analog methods as input data for this model. So for each event, for example, this event of here behind 2005, for each event we have 10 analog events. That I said before, that the analog events are events of the past that have similar atmospheric configuration. So for each event we have 10 analog events. We have the precipitation. So we introduce this precipitation of each analog event in the RIPS model, and we obtain for each analog an hydrograph. So for each event we obtain 10 hydrographs. With this 10 hydrographs, we perform an ensemble of hydrographs. That is a percentile graph. With this percentile graph, we have percentile 10, percentile 33, percentile 50, 66, 67, and 90. For example, between the percentiles 10 and percentile 90, the 80% of our predictions of flood will fall between these limits. So, for example, this is the best event, the best result of the 5 events that we have studied is the best result we have achieved. So here we can see that a significant portion of the observed hydrographs falls within the limits. So finally, as conclusions, as I say, the RIPS hydrological model has been calibrated to simulate the catchment hydrological response, and the analog-based methodology has been used to obtain a set of rainfall forecast that we use later to introduce as input data in the RIPS model. Then the forecast tool performs better when we introduce some antecedent precipitation into the model. And finally, as I present, the forecast provides a probabilistic distribution of potential discharge response on the Francolí River Basin for a given flood event. And this is all. Thank you.
Thank you very much, Daniel, for the nice overview of your work. It is perfect in time, so we can already switch to the next speaker. As I said, when you have question for Daniel or somebody else, write it in the Q&A field, and then we will discuss this issue later in the coffee break. But I have seen that Diana Jimenez turned on her camera. Are you giving the presentation? Hello. So she's talking about a multi-method approach to bridge resilience in the Baix River in Cauca, Colombia. I hope I pronounced it correct.
Yeah. So
Good.
you guys are sharing the screen, or am
I? Question to Eva. Here it comes.
Yeah, I don't see it. Yeah.
Give her a second. It started to share, and here it is.
Okay, yeah, we see it. So good afternoon. Thank you for having me. I want to talk about this project that I did with my professor at the University of Cauca in Colombia about remote sensing and hydrodynamic modeling on historical development for bridge resilience in Cauca. So this area is really special because in the early 2000s, late 90s, three strong visual events happened, also motivated by the volcanic and tectonic activities that not only cause infrastructural losses but also human losses. So that's why we wanted to start in this area. So what we did was first to collect information about these events that happened. Then we did the remote sensing part was to study to the Nevada volcano. For that, we download information from NASA, from Sentinel, and we do indexes and the advance. We could do an estimation of the molecular volume of water. So with that number that we got, we want to introduce it to the hydrodynamic modeling that we did on Hydras. For this, we especially studied a bridge called Coetano that is very important for the community. And for this basin, in this area, we did the hydrological characterization and the morphological characterization due to this is a very rainy area with very steep slopes that are very critical and crucial for when these events happen. For the hydrodynamic modeling, as I told you before, we use ECRAS 3D. For that, we found the results were very important. So with the remote sensing part, we found that approximately 460 million cubic meters of potential molecular water from the Nevada volcano. And with the hydrodynamic model, we found depths that were up to 4 meters, velocities that were from 25 to 30 meters per second, and shear stresses that were more 3,000 meters per meter. This exceeded the conventional design limits. So with this approach, offers a flexible approach for risk management in the basin. Yeah, so that was what it was about. Thank you so much.
Thank you very much for the interesting overview. I have a few questions, but that will come later. Thank you. Okay. Then, also perfect in time, by the way. So we are having time to discuss afterwards. But now we are switching from Colombia to Italy, to the University of Cagliari for Stefano, a reservoir-based representation of buildings for urban flood modeling. Stefano, the floor is yours.
Yes. Thank you very much. So, good evening or good afternoon or good morning to everyone. My name is Stefano Annis. I'm a PhD student at the University of Cagliari in Italy, but currently I'm in Germany for a research stay at the University of Siegen. In this short presentation, I will introduce a simplified approach to represent the effect of buildings and basement in urban pluvial flooding simulation using a 2D shallow water equation model. Buildings are usually considered as impervious because of the lack of data about the building's interior and also about the position of openings, and also for numerical reason. In fact, the correct representation of the flow inside a building will require a 3D simulation, which also, if the data are available, it's possible only for small areas. In reality, however, buildings are not fully impermeable, and the economical losses and also fatalities that happen during this kind of phenomenon sometimes are related to the water that enter in the buildings, and especially in the basement. The simplified approach that I'm presenting consists by represent the buildings by considering the external walls as impervious, but leaving some openings like doors through which the water can freely flow inside the building and outside based on the water levers. For buildings that have a basement, we represent it by using a reservoir-based approach. So the water that flow into the basement is removed from the computational domain until the reservoir capacity is filled, which means that the basement is full. After that, the water can freely flow inside and outside the building through the openings at the ground level. The approach has been tested using the rain-on-grid approach in the least flowed FP shallow water equation model. So I modified the code to include the reservoir-based approach, and as a case study, we consider a 2.8 square kilometers basin in London, representing the terrain using a digital elevation model with 1 meter resolution, and using as input a precipitation with a duration of 2 hours and a return period of 100 years. The domain is represented in the figure 1. We did the simulation 2 times. In the first simulation, we consider all the buildings as impervious with the reflective boundary approach, while in the second simulation, we use the proposed approach. Inside the Inside the basin are available more than 5,500 buildings. So also in the proposed approach, we consider half of the buildings as impervious, while in the other half, at least one door is present. The position of the doors and the openings are mainly retrieved from OpenStreetMap. About the 4% of all the buildings have a basement, and we consider all the basement with the same height equal to 2 meters. And the position of the basement were retrieved from official dataset of the City of London. In figure 2, I represent the results of the 2 simulation in terms of the map of Hmax, where Hmax is the maximum water level in every cell for a small portion of the domain, which is represented in figure 1 by the yellow rectangle. Looking at the maps, we can see that the 2 different approaches provide a different distribution of the water levers in the domains. And if we consider only the water outside the building, the proposed approach provides a mean level that is lower of the 40% compared to the fully impervious building. And we also obtain that the 29% of the pervious buildings are interested by the flooding with a Hmax of at least 10 centimeters inside the building, which means that the 71% of the pervious buildings, so of the building with at least one door, didn't experience flooding. We also obtained that the 41% of the basement are fully flooded, which might seem probably too high value, and this probably overestimation can be done also because at this stage we are not considering the urban drainage influence, which play a really important role in this kind of simulation. So this probably can explain, at least in part, this overestimation. However, in other parts of London, has been reported really high water levels in the basement during pluvial flooding. As an example, in the figure 3, there is a picture took in a basement with 50 centimeters of water, so half a meter, during a flooding that happened on July 2021. So to conclude, the presentation was about a simplified approach to include the storage effect of buildings and basement in urban pluvial flooding. The study is still at the beginning, but the initial results seem promising. And thank you for the attention.
Thank you very much, Stefano. Very interesting also about the sewer. I think there are a few questions approaching afterwards. And now we are switching back to South America, to Vicente. He will talk a little bit about the agent-based modeling of flood behavior. The study case in now it's getting tricky for me, Carampangue River in Chile. Is that correct?
So yeah, Carampangue River is.
Good, perfect. We're looking forward to your presentation.
Okay, thanks. Well, so thanks for the presentation. I am going to present the work we are doing with our group. We are trying to simulate with an agent-based model the interaction of people and floods in a real place situated in Carampangue River Basin in the central part of Chile. In this place, there are 3 communities that struggle with floods very frequently. Figure 1 shows basically how our model or our agent-based model works. We are trying to reconstruct historical dynamics in this place. The agents are household and the environment are floods. We are simulating a period of 40 years in total with a yearly time step. And our model relies on 2 main sources of information: 2D flood simulations, and the second, 2 surveys that have been made. And for simulating the interaction of people and floods, we are applying rules, and these rules are made for emulating 4 different behavior types, well-known, that are shown in the figure 2. And you can see more information in the paper from Lyon from 2018. And the outputs of our model are 2. First, the historical simulation at household level, from which household take flood-proof measures, and the historical simulation of household flooded. And we compare these results with information from surveys. And a question arises: which is the real behavioral type in our study area? And the answer could be it's in our results. In figure 3, we can see the percentage of household taking measures in the upper graph. In the below graph, it can be seen the percentage of household flooded in each year along all the period we are simulating. The lines are the 4 different scenarios, and the black dots are the observed data from surveys. In the upper graph, it can be seen that the black dots fall between the scenario Q2 proactive and the Q4 learning effect. This may suggest that the behavior in our study area are a combination of proactive and learning effect responses. And in the below graph, in contrast, the observed data aligns better with the Q3 status quo behavior. This contrast could be because of many reasons, such as the limited effectiveness of the household measures, and also by an underestimation of the flood model. In conclusion, we have a relatively well agreement of observed data with simulations. The real household behavior in our study area combines proactive and learning effect responses. It is still a challenge to attain simultaneous accuracy, and future work aims to refine calibration with more precise hydrological, hydraulic, and behavioral data to improve predictive reliability of our agent-based model. Thanks for your attention. I hope you understand.
Thank you very much, Vicente. Also from my side, there are a few questions I need to ask you afterwards because there are new, very interesting insights. And we move forward. By the way, so far, thank you very much to all the speakers for keeping the time. This is not every year like this, so it's very easy to chair such a session. And we are moving now to Thailand, to Supanon. And she sits at the moment in Poland at the Poznan University. She will talk about the application of incomplete topography information and public data for flood risk assessment. And she will talk about a study case of Klong Wat in Thailand. The floor is yours.
Thank you for the introduction. Good evening, everybody from Poland, but I'm originally from Thailand, and your pronunciation is correctly Klong Wat. So here I'm presenting the flood hazard mapping under data limited condition in Klong Wat, which is, look, do I need to wait for? Okay. Okay, so this is the flood hazard mapping with under the data limited condition in southern part of Thailand. The name of the river called Klong Wat and is located in the and the downstream of Klong Wat is situated in the urban area and very economic urban area as Hat Yai. Hat Yai is very vulnerable for flood event due to the tropical monsoon climate, rapid urbanization, low-lying topographic. And you can see the area of the river and location in the figure 1. So the technical challenge of this study is to use this limited data condition to reconstruct the bathymetry data. And because we lack of river bathymetry available and also very limited cross-section data that can be accessed publicly, and they are crucial for accurate hydraulic modeling. The main objective of this study is to develop flood inundation using incomplete topographic information and public data, as I mentioned before. So here we have 5-meter digital elevation model resolution, which is in Thailand in this location is the highest resolution available. And then we apply this digital elevation model to reconstruct the bathymetry of this area using the tool called terrain modification from RASMapper in HackRAS. And this tool is also used with the available very limited data for cross-section that only one point in Thailand to the inlet of Klong Wat. Then the one-dimensional steady flow was developed using the 30 years of peak discharge available from Department of Water Resources in Thailand. And we simulate 3 design flood scenario corresponding 10, 100-year and 500-year return period. One of the flood hazard map is showing in the example of the figure 2, which is 100-year of flood. In this area, in the small square, we can see that the different class that we apply in this flood scenario. So we also can see that the flood that affect the building that was exposed to the flood in this area is shallowest the flood class, which within class 1 with less than 50 centimeter deep. And the summarize of all scenario we can see in chart 1, which is the inundation zone in different scenario. From the chart we can see that all scenario, the most vulnerable area is within the flood, is within the class 4. But the area, the flood, the building that affected by flood is start to be vulnerable in the scenario of 100 and 500-year scenario. And to conclude this study, we want to show that even very limited data, we have only 5 meter resolution of digital elevation model and only one point of cross-section data, we still can have the flood hazard map, and it's essential for the emergency response planning, land use regulation, and long-term flood risk management. Especially in this area, if you look in the news recently, just last week, Hat Yai experienced one of the worst floods in the history, and also in the Southeast Asia region. So I hope this study can develop further in the future, and we can have the better simulation to help the area can be reduced in flood event in the future. So thank you for your listening.
Thank you very much for the presentation. And you already gave my comment. I just wanted to say, when we have a look to the news currently, then we see how much damage we see due to flood events in this area. At this moment, also, like hearty welcome to my colleague Tomek, who is in the auditory, for listening your presentation. And we will move further. We were moving now to the University of Ottawa. I told you, we have here participants and panelists from all over the world. It's Reza who will talk about the coastal infrastructure protection against tsunami inundation, the Merkel modeling of a novel countermeasure. The floor is yours. If you're in the room. Reza, I have not seen you so far. Are you here? Then I will ask my first officer, Eva, have you seen Reza in the room?
No, so far not. I can check on the chat, but I don't think so.
Otherwise, I would say we move his presentation to the end in the case he will join us later. And we would come back to the other side of the world, to Dimitri. Are you here? Yes. From Moscow, development and testing of method for estimating probable maximum snowmelt and probable maximum river discharge during fresh head periods. The floor is yours.
Good evening. I'm Dmitry Kirillov from Lomonosov, Moscow State University. I'll present a study on new method to estimate maximum possible snowmelt and maximum possible river discharge during fresh period. Traditional flood risk assessments in Russia rely on statistical approach, which ignore physical limits of snowmelt runoff. These limits are caused by maximum potential radiative energy available for snowmelt. Main aim of my research is developing and testing physical method for estimating maximum probable discharge. Method for calculating maximum probable snowmelt adapts heat budget model invented by Soviet glacialist Kuzmin with ideal conditions that maximize radiative energy input, and equation 1 in the slide. We use this equation for 109 weather stations in Europe and Russia and make graphs. Figure 1 is example. Colorful lines are maximum snowmelt that obtained with equation 1 for every day from February to April. Black line is maximum possible snow water reserve for this period. And point of intersections of this line is actual value of maximum probable discharge. Of maximum probable snow, I'm sorry. And this value is limited by snow water reserve. So to estimate maximum probable discharge, we use equation 2 in poster. So for 109 weather stations, we obtained values of maximum radiative snowmelt and its values range from 40 to 56 millimeters per day. Then we try to find relation between maximum snowmelt and latitude or date of maximum snowmelt. And there is linear dependence between maximum snowmelt and its date in figure 3. Then we calculated maximum discharges for 7 field basins in Europe and Russia. So calculated discharges significantly exceeded historically observed values for 6 cases. But for Chapayevka River, it's wrong. About conclusions, maximum possible date of snowmelt is related with time course of maximum snow water reserve with linear dependence, but not related with latitude. And estimated maximum discharge values are actually more than observed in the most of cases, but not all. So we have to calculate not only radiative heat energy, but also turbulence heat exchange, because it can play an important part in the process of snowmelt. And so our method has potential to estimate physical limits of maximum discharges, but it needs an improving. So thank you for your attention.
Thank you very much, Dimitri, for your explanation about the snowmelt. I'm pretty sure that there are questions about that also. So please use the question and answer sheet. Last reminder, because we are heading to the final of the presentations. But when we're heading to the final, then we are moving to Iran, to Masha. Masha or Masa? Now you need to correct me if I pronounce it wrong, because she will talk about enhancing probabilistic flood mapping with Sentinel-1 SAR and NDWI case studies from Bolivia, Spain, and the US. Just a moment, you are muted. We can see you, but we don't hear you. Can you give us a small sign by hand if you can hear us? So give me a second. Eva, can we remotely unmute her? I have no permission to do that.
I'm not sure. I can try. I can ask to put the sound on.
That would be great.
And that should hopefully work. Ah. Still can't hear you. Now your mic is definitely switched off.
Eva, maybe one more try.
I don't know where she's gone.
Okay, I see her still.
I need to try to find her again. Here she is. No. Can you say something, Masha?
That's a pity now. You know what? I would change the speaker order and would you put you to the end, so we are not kicking you out. It's just you put it to the end. Maybe you can solve in the meantime something with the mic, or you just re-log in, because when I logged in today for the first time, I also was unable to do anything. Maybe that helps.
Yeah, maybe just come in, and when you come in, please raise your hand again, so I'll find you on the
attendee
audience.
list.
Yeah.
Good, then we do it in this way. Then we would move further to the estimation of vegetation height from UAV. Chivai, are you here? Do I pronounce it correct?
Yes, yes, pronounced correct.
Perfect. From the Polish Academy of Science, the floor is yours.
Thank you.
And the presentation is also there in a few seconds.
Okay. I cannot see the poster.
It's coming.
Okay.
Here it is.
Yes, I think yes.
Good.
Can you make it bigger? Maybe the foreskin. Okay, I begin. Hello everyone, I'm Iwei Guo from the Institute of Geophysics from Polish Academic Science, and my presentation is estimation of vegetation height from UAV. Against the background of climate change, extreme flood events are becoming more and more frequent. The significant damage caused by the flood has highlighted the necessity of developing a reliable flood management. As a basic tool for representing the flood process, the hydrodynamic models are typically driven by fixed roughness parameters and ignore the fact that the roughness changes by the dynamic vegetation, because the vegetation will change seasonally, and sometimes it will damage in very short times due to the hazards such as the flood or dry, and this will causing the uncertainty in the modeling results. And therefore, this study aims to establish a relationship between the multi-spectrum index such as the NDVI, LCI, and other index, which can be calculated from the remote sensing imagery, both from the satellite imagery and drones imagery. And my aim is to establish the relationship between this kind of index and the vegetation height, because the vegetation height is very important parameters to calculate the vegetation roughness, so that in next step I can get the real-time vegetation roughness from the satellite imagery, instead of go to the field measurement to get the real-time vegetation conditions. But now, most existing research on this topic estimates the roughness for the single land cover types, while these studies aim to estimate it for the multi-counts. We will not do some classify before training. And in these studies, we selected two sandbars which located in the ridge between the Dublin and Grosjean of the Wisła River. During the flood events, these sandbars may be overflowed, which were increasing the flood resistance and influencing the flood process. The logistic growth covers and the random forest method are used in these study areas. The LGC is more suited the vegetation growth conditions, and it is trained by the single index, while the random forest used all of the index I selected to train the relationship, and the random forest has been widely applied in the research and can estimate the vegetation conditions very good. And we can see the results. The results show that in the study areas with the complex vegetation conditions, the LGC performed unsatisfactorily because the R-square is around the 0.10 to 0.10 to 0.23, but and the CL green performs the best among all the index. And from the random forest model, we can see that it can effectively explain the vegetation conditions because its R-square is high, around 0.7. But since the data because I collected this data from the single days, since the random forest model seems performed good, but it is lack of the date. So in the next step, I will collect the data from different seasons in 2 years, just different seasons and different times, and to ensure the trained model can be applied to the different study areas and the predators, so that the vegetation height and the roughness can be directly estimated and applied to the flood modeling by the importing index driven from the saddle imaging. Yeah, this is all. Thank you very much.
Thank you very much for the presentation and for the insights. Then I would like to switch to the next speaker. We go now to Berlin, so to Germany. Fast prediction of heavy precipitation induced runoff in an urban area. So we are again in urban areas using deep learning methods. It's Sangchai. Did I pronounce it correct?
Unfortunately, no.
I missed it. Help me. How is it pronounced?
Yeah, it's pronounced as Sangaj.
Sangaj. Okay,
Yeah.
that's new.
Yeah.
Good.
Yeah.
Sangaj, the floor is yours.
Yeah, thank you very much.
You're welcome.
Yeah, thank you very much. Hello, everyone. My name is Sangaj from Technical University of Berlin. Today, I will be presenting my master thesis topic titled as Fast Prediction of Heavy Precipitation Induced Runoff in an Urban Area using Deep Learning Methods. So as we all know, urban flooding has emerged as a critical challenge in this 21st century. So the conventional response to such flooding events focuses more on reactive measures, whereas modern approach focuses more on proactive preparedness. So how do we ensure that we are proactively prepared for such kind of flooding events? For that, we need predictive strategies and methods to forecast flooding events in advance. And yes, various techniques exist, such as the 2D hydrodynamic shallow water model, which are really highly accurate, but they are computationally intensive. And this computational demand limits their timely application in urban contexts. So this study addresses this challenge by providing 3 alternative methods for predicting urban runoff by analyzing 5 flood-prone locations in district area in Berlin using the synthetic data generated from the hydrodynamic model HMS++. So the 3 methods that I used in the study are a simple linear regression model, which gives you a maximum water depth prediction, a single value based on a certain amount of rainfall height. This is the rainfall distribution process can be seen in figure 1a, which was used for the simulation, and the result of the simple linear regression model can be seen in figure 2a. The x-axis represents the actual water depth, which is from the hydrodynamic model, whereas the y-axis is the predicted water depth from the linear regression model. The second method, scaling and interpolation method, gives the time series prediction of water depths. And the rainfall temporal distribution of the rainfall can be seen in figure 1b. So we basically interpolate the water depths values based on the rainfall height. So example, let's say a rainfall event that happened in 2008 had a rainfall height of 34 or 35 millimeters. We used 30 and 50 rainfall heights to interpolate and get the prediction. And the third method is based on the deep learning approach, which is based on the architecture of time distributed 2D CNN and LSTM model. So a total of 20 rainfall events were simulated in the hydrodynamic model. The rainfall events distribution can be seen in figure 1b. We had different heights such as 20, 30, 50, 70, and 90 rainfall heights with 4 different categories. Like we had front single peak, we had middle single peak, rear single peak, and then we had uniform peak. So Gleim tunnel location in figure 2c can be seen. That was the primary hotspot, as it's one of the most prominent flooding areas here in Berlin, and that's why it was chosen as the study area. So from this figure 2c, we can see that there's a blue area highlighted. That was the specific grid area that we defined during the simulations, and from this grid, water depth values were extracted and recorded at every 10-minute intervals, corresponding to each cell, with each cell having its own water depth uniquely identified by the spatial indices. And meanwhile, the 1 hour rainfall data was aggregated into 6 different time steps. So finally, we had the data set X, Y indices and rainfall heights and the water depth data in the data set. And of course, the model was trained on this data set, and we had predictions which can be seen in the results, figure 2D. So on the left, we have the third interval because the rainfall that happened in 2008 had the highest peak in the third interval, which means from the 20th to 30th minute. That was the actual value predicted by the hydrodynamic model, and the middle figure shows the predicted value, which is predicted by the deep learning model. And of course, the third figure on the right is the residual between them. All in all, we had a good prediction R2 score for this method of 0.88 and NSE score of 0.88. And to conclude, we can say that simple linear regression model predicts single maximum water depths really well, and scaling and interpolation method captures the overall trend, though a minor temporal lag is present. The deep learning model captures the overall trend of water depth fluctuations from both spatial and temporal distribution, though it tends to smoothen out extreme values. Yeah, thank you very much.
Thank you very much. Now I try it again, Sangash.
Yeah.
Good. That's good. So it's also nice to meet new people and to learn new names and to know to pronounce them. And now we will ask Masha if I pronounce her name correct, because I think the mic issues are solved now.
Yes, can you hear me this time?
Perfectly.
Yes, sorry for my microphone. And if you are ready, I will start.
Here it is. No, it's me in big.
Yes. Yes. Hello, everyone. I hope you are all doing well. In this short presentation, I want to speak about enhancing probabilistic plot mapping with Sentinel-1 star and NTW.
I'm having some connection problems. Is it only me? Then I will write her briefly in the chat.
I think she somehow fell out again.
I saw that she was there with two profiles. I think one for sound.
Yes. So now she's back.
Excuse me. Have any problem?
Not a problem. Please,
No problem.
please start where you were. No problem.
Can you, excuse me.
We hear you now. Eva, can you share the presentation once more?
Yes. This region represents different climate and land cover characteristics, making them ideal for evaluating their robustness of method. Our workflow consists of four key steps. At the first, we use Sentinel-1, SAR, BV, and VH polarization and compute NDWI from Sentinel-2. We incorporate land cover classes from the Copernicus Global Land Cover dataset, including forest, wetlands, agriculture, urban areas, shrubs, herbaceous vegetation, and bare land. At the next step, using samples from SEN1 float is 11, we extract SAR backscatter and NDWI value for each land cover types for both training and validation. And finally, we apply local percentile threshold 5 to 95% specific to each land cover classes to generate pixel-wise float probabilities. Model performance is evaluated using prior score, expected calibration error, and reliability diagrams. This entire workflow is operationally implemented in Google Earth Engine, enabling near real-time flooded monitoring. As a result, across the 3 cases study, at first SAR-only model performance, prior score as a result is 0.226 and the ECE 0.1737. For SAR plus NDWI model performance, barrier score improved to 0.209 and the EC improved to 0.169. This shows that integration in NDWI leads to the better calibration and lower uncertainty. Looking at the specific land cover classes, shows that for urban areas, barrier score decreased from 0.25 to 0.23 and wetland 0.27 to 0.24. Forest and agricultural areas also showed consistent improvement. The integration of NDWI helps reduce false positive in urban and agricultural regions and enhance flooded detection in wetland and forested areas, places where SAR alone can be ambiguous. Visual inspection of the probabilistic maps also shows that the combined SAR plus NDWI model produce more realistic and spatially consistent flood pattern. And for the conclusion, our results demonstrate that combining with NDWI significantly in the heterogeneous landscapes. Reduce false alarms, improve detection in complex environments, and provides continuous likelihood maps suitable for real-time applications. Limitation merely related to the cloud contamination in Sentinel-2 NDWI, but the benefit outweigh the drawback when combined with SAR. For future work, we plan to incorporate topography and hydrological constraints and test the method in additional regions and explore higher resolution and higher frequency satellite observation. Thank you for listening, and I will be happy to answer any question.
Thank you very much. In a few moments, it was a little bit bumpy, your connection, so I need to ask a little bit further in the question session. Last call for Reza from the University of Ottawa. Reza, are you here? Please raise your hand.
I don't see any hands on the audience, so probably not.
Me neither. But that means now it's time to go to the relaxing part of today, at least for you, because for us it's always relaxing to listen, but I think to present in such an auditory with so many people, so many attendees, is a little bit, the moment where people are getting nervous. I hope it was not for you. A little bit of tension is okay, but there's no reason to be nervous because we are one community and we are here to help each other and to learn from each other and to exchange with each others. So I would like the speakers, the panelists, to turn on your cameras because now it's the time to shine. Because first of all, I would like to thank all of you for the excellent presentations and for the insight in your work. I think this is a very important moment always when we are conducting research because we're sitting in our offices all day long, sometimes also during nights. We're out in the field, independent of the weather. Most people think fieldwork is like sitting in the sun and enjoying it. But most of the time when it's getting interesting, then it starts to rain, then we have flood events, and then we are out in the field when others stay at home. And I think such a congress or like this young professional congress like we have today, I think this is the moment where we can shine, where we can show our results and where we can be proud about the last months, weeks, and years what we worked on it. And I always think, or at least my impression is always in these moments, all these things are forgotten, the long nights in the office, the bad weather in the field, because this is the time where we present our work, where we show what we did. And I hope you have the same feeling and you did very well. So congratulations from our side. This is, always a nice moment, especially to see how young researchers do the research, what are they presenting, and to make it a memorable and enjoyable event. Also, like one more thing I would like to hand over or to give you, because your presentations were all in time. So first of all, this is the first time it happened to me, because as older the presenters are, as longer they want to speak. This is the problem. So I see we have here now a change. And the second thing is about your posters. They were all very nicely made, because in the first Young Professional Congress, you see Eva puts up her thumbs. In the first Young Professional Congress, we have seen really other things, I have to say. So this is also one step forward, and I think in science, because usually we do our science, we do research, and we forget that we need to sell what we did. And making a nice presentation, making a nice poster, this is the part where we are selling our work, and you did very well today. So congratulations from my side. But now I think it's also time to ask you a few questions, and maybe you want to chat in between. So maybe you have seen things from others, because we have people who worked in urban areas to talk a little bit about that. So it's time for the question and answers. I have seen there were not many questions in the question and answer field. This is why we are coming up now a little bit with the question and answers. And I would like to go in the same order as we did during the presentation. So I would like to start with Daniel. Are there questions for Daniel? Most of the time, I know the presenters are nervous when they're giving their presentation. They're prepared for that. They're not listening that much to other presentations, but sometimes there are questions arising. Then I would say I would start a little bit with a few questions. So you had this one hydrograph, what you calibrated, and then you had this ensemble with 5 hydrographs. What I did not got 100% is this 5 hydrographs, what you had then. Are these also events which happened, or are these artificially made hydrographs?
No, all the events are events of the past are real events also. And are the five different events that we calibrated, but that are real hydrographs. And I don't know if you have other question about this.
No, that was a little bit the question, because I think this approach is very nicely, because then you're giving this band and you have different hydrographs, what you investigate. So because they were rather different, and I think this is an important thing also, like for the future, what you have shown, that very often our models are calibrated exactly on one hydrograph, and we try to fit them as long until they fit perfect. But you don't know what happens if the event looks a little bit different, because what we experience in Austria at the moment is that the events look rather different from year to year. So in the past, we always had this 1-year flood event, we had this 100-year flood events, and suddenly we're getting completely different flood events or different shapes of the peak. So it's not a flood event with a peak anymore, it's a peak and then it stays for a long time. And in 2019, we had a flood event where we had a 1-year flood event, or with a return period of 1 year, and it lasted for 30 days, which was never there the case. So I think this approach is very, very nice. What you did with this band, that you said, okay, we have 5 hydrographs.
Yeah, thank you. And also we have a problem because in this place we have a few events recorded, because it's a place that is difficult to record.
Yeah.
And we can't calibrate as much events as we want. So we only have 5 for this, because we have less events. But well, we think we more or less could reproduce the reality in the model, more or less.
Okay. So is it because it's a data scarce region where you don't have a lot of monitoring stations, or is it only a short time where you have observations?
It has stations. I think it's 6 stations, but and have data since small. Some 1 or 2 lines since 1990, others since 2000. But the problem was that this is a place where it's characterized by flash floods. And sometimes these flash floods were not properly recorded, or and also we have a less small cases. So.
Okay. And this is getting tricky also for the future. It's a good point what you made. Also, when we have measurement stations and monitoring, we need to see if we can capture the flood events, because as you said, flash floods occur very quickly, and suddenly they're disappeared and the damage is high.
Yes, for that we think that some calibrations we could do it properly, but others not, because of the floods. So.
No, I see. Are there other questions? If not, then thank you, Daniel, for answering. And then I would switch. Diana left, so if there are questions for her, she sent her email in the chat, so you can contact her about her poster. And I'm pretty sure that all of you are open for questions. So if there are people who are interested more in your work, please contact the authors. This is the moment to exchange. And I think they're all open for an exchange. And these are also the moments when cooperations develop, just to say that also like for the future already. But then we will go now to the urban areas to Stefano, where we have seen, how many basements are there in London and how can you use them for storing water? Stefano, are you here?
I
Here he is.
have a couple of questions here.
Yes.
So, Stefano, you said that you got the openings for the buildings from OpenStreetMap.
Yes.
And I was wondering how precise you estimate this information is, and also estimating how many basements you have. I'm wondering, how much information do we really have about the volume of the basement of buildings?
Yeah, for the basement, for the position of the basement, the position is from official data set of the City of London. So I think that at least the position is correct. The problem is that we only have the position as point. So I consider the area the same as the building, but of course it's not sure that this is the reality. And yes, I think that one of the main reasons why the buildings are not included is the the lack of data. About the openings, I said that most of the position were retrieved from OpenStreetMap, but I didn't indicate it by hand. I mean, you can download the data that usually are made, I think, from the owner of the building. So I check it with Google Earth, and usually are quite good. The problem is that usually there is only one opening for buildings. So, of course, it's not precise. I mean, we can just include the presence of maybe one door and not of the other doors or windows and so on. But yes, I mean, consider all the buildings as fully impervious. It's not correct, because we know that a lot of times the water can enter. So we are trying to find a simplified approach to at least with simplification include the effect, yes. But the availability of data is the main problem.
Yeah. I mean, it's really a wonderful approach to include all of that storage area that is there with the buildings. So yeah, congratulations on your work.
Thank you.
I just wanted to ask, is also Downing Street number 10 in your area?
No.
Ah, too bad, because I wanted to know how big the basement there is for the Prime Minister to store his stuff or her stuff.
Probably it's quite big.
Maybe it is. But I also thought about you had in your model like 4% of the buildings had basements. This is
Yes.
what I got. Okay. Is this usually in London that not many buildings have basement, or is this the information you had?
It's just information that I had about this building.
Because the older cities usually all or many houses have basements, but
yeah, but we just focus on a really small part of London. So I mean, 4% of 5,000 buildings are a lot of basement.
It is, and it's a lot of storage volume. What do you have? Perfect. Thank you very much.
Thank you,
Vicente. You're the next one. I have a question about the Levy effect. Yeah, maybe because you didn't explain the 4 different cues, but the Levy effect, to have this correct in mind, this is when the people are feeling safe because they have a levee in front of their house.
Yes, you are correct. People who, they expect they are safe, and they forget that the place in the reality is unsafe, and that's the Levy effect.
Because this is the big discussion what we also have in the Flood Risk Management Technical Committee about the levy effect and so on, because we see in many countries where levees are built and the mayors are really standing there in front of their people and say, now we're 100% safe. And I think when we learned something in the recent years due to climate change, that we are not 100% safe. There are always a situation which is bigger than what we have expected.
Absolutely.
For your, sorry.
No, let's go.
Yeah.
Go.
Just go ahead. It's
No, but you're all right. I think I agree with what you're saying. So
I have another comment or maybe question on you said that you got the behavior of people from surveys. And I was wondering, how honest do people report on their intended behavior or real behavior in terms of safety measures? What's your take on that? How do you feel how they do that?
Okay. I think the people were answered which are the measures that they were taken. So and we take this, and then we categorize people that this people is or has a behavior of proactive, or this person is more status quo. They don't take measures. So that's the way we categorize people.
And are people, you mentioned that people, or you mentioned that sounds a little bit bad, but do you really expect that people are telling you the truth?
Yeah,
this was the question from Eva a little bit.
It would be difficult to think that it's always true, but I think more or the most part of the surveys are true. They are not telling.
Yeah, I totally agree. But I think this is always the nice thing on being an engineer, that we have data, and data usually don't lie. And when you're working in social science and you're making such interviews, then you always have a little bit a problem. There was a recent studies where they asked people how often they fly by airplane, and people said never, because it's bad for the climate. And yeah, the airplanes are all full and occupied when you want to book one. But this is always a little bit this tricky situation. But I think it's really interesting to see these 4 Qs and to see where people are, because this is also something what we want to shift. Meanwhile, is to go away from that the governmental institutions need to take care about people to 100%, because I think to take care by themselves, also they should protect themselves a little bit more. This is very, very important, and also to be prepared for the flood event.
Mm-hmm. Yeah.
Good. Thank you very much.
Thank you.
So let's move to Thailand again, to Subanon. Are there questions for her? Because otherwise I would start. So you said you had a DEM with a resolution of 5 meters?
Yes.
Yeah, which is very high. So we're not in the data scare region anymore. So there are some parts where I modeled by myself where we had a resolution of 50 to 50 meter of the data point. So 5 to 5 is very good. But my question would be a little bit more to the bathymetry, because you said you interpolated from the DEM because it didn't have cross sections. Did I understand it correct?
Yes, but we have a cross-section in one point in the inlet of the Klong Wat. So we use that cross-section measurement to apply in the terrain modification.
Okay, so you had one cross-section, and
yes.
The rest of the cross-sections you took from your data, what you had from the DM.
Yes.
Okay, that was a little bit the question. Did you calibrate your model somehow?
The calibration and validation is not yet exist. Yeah.
Okay. Because you don't have data for calibrating and validating?
Yes. Right now we don't have the data for calibrate, but for this flood event, which is the different scenario, right? Different effect for this model. But maybe we can start to collect, because the area that affect now is very huge, and also include in this area.
Yeah.
In this area of mapping.
Because this would also be like a little bit the recommendation that you check out for such data to calibrate. It doesn't need to be that accurate data to have it very precisely, but at least when you have a little bit the impression how good your model works, then you have the first reliable predictions with your model. That is a little bit what I have seen, because you also talked about the inundation class 1, 2, 3, and 4.
Yes.
1, 2, 3, 4.
But from my previous profession, I working there. So I have a roughly idea. So we see we don't have like written historical data, but we have seen the area flood. So me and my colleague see this model is correct, but we didn't have a scientific or written official data to calibrate and validate them.
Yeah, but this is citizen science. So when you know what you have, then you can take that into account, and you can also like write it down and name it like that, like citizen science inspections. Because this is something where we have data scare regions where we really belong to, where we go then and ask people about the flood scenarios. So we have here in Austria the Disaster Competence Center. So they are always invited by the United Nations to travel to areas which were flooded, where they really ask people and ask really like on a tree, how high was the water? And in the end, it doesn't matter if it was 20 centimeters higher or lower. You have at least an idea how good your model is and what the flood event gave.
Yes.
But that is something what I would recommend you use that information and also show it there and say, okay, we calibrated on that. Maybe it's not 100% replicable, but in the end, you have at least an impression what is going on.
Okay, thank you.
Citizen science. This is the thing. Also, like for all of you, when you're somewhere, you're observing a flood event or something like that, always think about such things. Meanwhile, we all have our mobiles with us, make a few pictures. Maybe there are scientists which model these flood events and they are happy about such pictures and about such indication. This is something what we can share and what we are using.
Are there other questions? If not, then we would switch to Dimitri. Are there any questions about snowmelt or on snowmelt? Then I will also start. You see, I'm very curious about this thing. Sometimes, sorry to say that, I will say it in this way, there are no stupid questions. I need to say that now because I'm not an expert in snowmelt, but I will ask questions just on curiosity. And I think this is something what we scientists are, curious people. Dimitri, when you talk about your snow melt, you only consider this the snow melt, and how is then the process from snow melt to runoff? This is what I didn't got 100%.
Thank you for the question. When I talk about snowmelt values, I mean snow water equivalent of snow that melted.
Yeah. Okay. And do you also consider that when the snow is melting, that you have somewhere reservoirs inside your area? Because your discharge was in some cases higher than the amount of water which was melted by snow. So I'm wondering where is this water going, or where is it stored? Do you have some reservoirs beyond the snow cover?
Do you mean as sources of water?
Yeah.
Yes, it may be liquid precipitation, rains.
Yeah.
But I won't use it in my method because when I calculate maximum snowmelt, I use ideal conditions and to maximize short radiative energy input. And one of these conditions is clear sky, so zero cloudness, and so it there can't be rain. And now to improve my method, I already calculate turbulence, and now I guess it's discharges that were obtained with radiation and turbulence energy input. They significantly exceed all absurd discharges.
Okay. And because this maybe a quick last question, because you said you're not having a cloudy sky, but in the end, when you have the snow melt, you have too much calculated discharge compared to observed ones. Did you also then think about reducing the clear sky a little bit, or say when I have 10 hours, then I have 3 days or 3 hours cloudiness and 7 hours clear sky? That this is a calibration factor?
No, because that I obtain, they are ideal. It's maximum discharges can't be so high. It's limit. And my task is to physically limit these values.
Okay, that makes sense. Thank you very much for answering.
Thank you for the question.
I would move further to GY. Did I pronounce it correct now again?
Actually, it is Yiwei. Yiwei. Yes.
Yiwei.
Yes, Yiwei. Yes.
Then I know now.
Thank you.
Good. Are there questions about UAVs and vegetation? Now, Sangash.
Yeah, hi. I just had a small question regarding the flight parameters. What were the flight parameters that you chose for conducting the UAV flights?
I use the 19 meters and other parameters. I think it is the automatic one in the drum directly. Yes, and change the angle of it to make it, because I fly it's not very high, so the picture is very, very much. So I just choose the angle that it will not take so many pictures and let it fly. Yes. Actually, I only take the half of the sandbar because it is too big for this height. So next time I will, in my further research, I will change the parameters, maybe make it to 150 meters and then to, yes.
Okay, yeah, thank you.
Thank you.
And thank you also from my side for the introduction, because you gave a very nice introduction about the vegetation. And I had last week a hydraulics exam, and this was one exam question. What about the vegetation and the Manning roughness in the equation? But this is also the question what I would have to you, not an exam question, no worry. About your vegetation, did you recalculate it also like the Manning value with and without vegetation to have a roughness?
Yes, actually, my final aim is to get the Manning's roughness because the hydraulic models I used is the Delft 3D FM, and it used the Manning N to do the simulation. So my final aims is to get the Manning roughness. But when I try to calculate it, I find that I didn't have the vegetation height. Because in my first step, I just want to get the information from the settling imagine. And then I find that it is not enough because I cannot get the vegetation height information from the settling imagine. So I turn to the drone and then to calculate the Manning's N. Yes.
Okay, good, interesting. Because I think this is then for the modelers the important parameter where they are eager to have a correct one also for different vegetation times and of course also the spatial distribution. I think UAVs will provide us in the future very good insight on that. Thank you very much. If there are no questions, then Sangash, you're already stepped on the floor. So maybe there are questions for him too.
Actually, I have one. You mentioned that the linear regression model was the most precise, and I was kind of wondering, when you do linear regression but you have non-linear processes, how you came to this model being the most precise, or this regression being the most precise, or what your take on this is.
So the linear regression model, so for that, total 24 rainfall events were simulated. So after the simulations, only the maximum water depths were extracted. So only a single value from each rainfall event was taken up. And those 24 values exactly were like in a linear pattern, I would say. And that's why it fitted very well. And also, regarding, like, I don't know, like for the nonlinear patterns, how will it will turn out? But yeah, that's for like further to study.
Yeah, thank you.
Good. Are there other questions? I just have a question, a monetary question, of course, as usual, because time is money. You wrote that you accelerate the process because you also wrote that the 2D models take a lot of simulation time. What would you guess? What is the time what you could save with your approach?
For the deep learning approach, the prediction time is in milliseconds.
Okay, so long.
Yeah, quite long.
Good.
Yeah, and the training time is 1 minute or so.
Okay, but how long would you need to set up the model in total?
I mean, for the input data, we have to prepare the input data and then we have to train the model.
Okay.
And that takes 1 minute or so.
Okay. Yeah, because like setting up the 2D model takes already a month, and then simulating takes again a week.
Yeah,
and then
the simulation on the hydrodynamic model takes months. Yeah.
Exactly. Yeah, it depends on the model and on the model length, of course. But this is a little bit the question. And how transferable are your results to another area?
I think this needs to be properly validated, because currently in my study I used only that specific grid that you saw in the photo, that the blue grid. And of course, if we have to take into other locations, we have to validate the machine learning, the deep learning model.
Okay.
And so for that, I would also need to train the model again on that location's data, and then we can have predictions there as well.
Yeah, good, but this is not a problem when you have 1 minute for training and then 1 millisecond for simulating. Then I think this is the time which is very good invested.
Yeah.
So perfect. Thank you very much for giving the insight. Masha has left the room. I don't know if she came back.
She wrote that she has connection problems and might not be able to rejoin.
Okay, good. Because then we will end the session here. So the EMI committee was 3 minutes long and we were 2 minutes too long. So it's a little bit longer than expected, but I think it was worth about that. Manish, are you also here? Because then we would make a last group picture if that is okay for you. Then I will press the button. All have here he is.
There he is.
Have you seen he's already with suit and tie on the way? He's already done for the day. All make a little smile and make a picture. Perfect. Thank you very much. Not only for the picture, thank you all for participating here in this event. Just need to store it. Thank you for participating. Thank you for presenting your research. I think this is the perfect opportunity. Also, like to network. If there are questions, then write to your colleagues. I hope you had a good days, had good 3 days. We will also continue tomorrow with a flood risk management session number 2, because we have so many submissions this year. We had so many that we had 2 sessions. So if you have time tomorrow and no other plans, join us. Very interesting presentations. I already had a brief look. And otherwise, I would say thank you very much for participating. Thank you for your work. And I hope we will see next time, maybe in reality, in an IHR Congress. And when we are meeting for the Flood Risk Management Committee meeting, then just join and for a small exchange. And maybe you're interesting to work with us or to support us. And then we can or we are open for that too. So in the end, we would be happy to connect. Have a nice evening. Have a good morning. Have a good night. And then see you around. Bye-bye.
Thank you very much.
Also, thank you very much, Stefan, for chairing the session. Thank you all panelists for giving wonderful presentations today. Also, thank you everyone in the audience for holding out and being here and supporting this and learning from each other. And I invite you to come back tomorrow and we'll do one more day of really exciting presentations. You already heard that it will be another session on flood risks, but we also have other sessions, really a wonderful variety. And I hope you have a wonderful evening or rest of the day, and I hope to see you tomorrow again at the YP Congress. Bye.
Thank you, Eva. Bye-bye.
Recording stopped.